In this example, we have an RLC circuit and we know the values of R, L, and C. What happens in this problem is that it begins with the switch set to position A, current is allowed to flow, the capacitor becomes fully charged, and then at t equals 0 the switch flips to position B. So that happens at t equals 0. The first thing we're asked to find is what is the oscillation frequency of the circuit once the capacitor has been charged and the switch is connected. So what we have to do is come back to our equation for the charge on the capacitor plates and use our expression for the angular frequency of the RL circuit and calculate that frequency. So omega equals the square root of 1 over LC minus R squared over 4L squared. The values we have to plug in, L is 22 millihenries, so that's 22 times 10 to the minus 3 henries. Our resistance R is 75 ohms, and our capacitance C is 15 nanofarads, which is 15 times 10 to the minus 9 farads. Put all those numbers in, and what we get for an angular frequency is 55 times 10 to the 3. The units are radians per second, or just seconds to the minus 1. Now, it doesn't ask for angular frequency, it asks for frequency. So all we have to remember here is that omega is equal to 2 pi f. So f, the frequency, is omega over 2 pi. So we divide our 55,000 by 2 pi and we get 8.76. times 10 to the 3 seconds to the minus 1, or hertz. Okay, there's part A. Part B, how long will it take for the amplitude of the oscillation to decay to 10% of its original value? Let's make sure we understand the question here. So this is the amplitude of oscillation. That means if we thought about the charge on the capacitor plates, it oscillates up and down kind of like this. And the amplitude is this dashed line out here. The equation for the oscillation is Q of t equals QO, the maximum or initial charge, e to the minus r over 2L times time, times cosine omega t plus phi, where phi is a constant and Q naught is our constant. The amplitude of oscillation is this part. So this is the part, oh, I shouldn't have highlighted this. This is the part that represents the amplitude. So what we're trying to solve here is when our charge is equal to 0.1 times the original value. So for our amplitude expression, Q of t equals 0.10 times QO. So that's the new amplitude. So we'll say 0.10 times QO equals QO times e to the minus r over 2L times t. Our QO's cancel. We've got 0.10 equals e to the minus r over 2L times t. Take the natural log of both sides. And it asks how long, so we're solving for t here. T equals 2 times the inductance times the natural log of 0.10 divided by the resistance R. We'll put in our numbers. We know R and we know L. And what we get for our time is 1.35 times 10 to the minus 3 seconds. So it doesn't take that long to die off. Part C, what value of R, so if we take out this resistor, put in a different resistor, what value of R would give us a critically damped circuit? So here we have to remember our definition of critically damped. So critically damped is when we change our resistance, we still get the motion dies off, but it doesn't oscillate. So that's what critically damped means. So a damped oscillation Let's just draw those two pictures. A damped oscillation is one that it dies off over time, but as it dies off, it oscillates. So this guy is damped. The one that's critically damped dies off, but doesn't oscillate. So this one is critically damped. This one has an oscillation, so omega is not 0. Omega is given by our expression here. This one does not oscillate, so omega is equal to 0. So let's fill in that 0 is equal to 1 over LC minus r squared over 4L squared. Take the square root of that. So we know that this is going to equal 0, so let's solve and see what we get for r in this case. So we'll square both sides. 0 equals 1 over LC minus r squared over 4L squared. Bring the r squared term to the other side. So r is going to be 4L squared over LC. Take the square root of 4L over C, or 2 times the root of L over C. We know that L was 22 millihenries. And we know that C was 15 nanofarads. So that gives us a resistance of 2,420 ohms. So if we pop in that resistor, the oscillation will die off very quickly without oscillating.